Okay, morning everyone. So we'll start off our class here with a quick warm-up question again. This whole chapter we've been focusing on naming different compounds. We steadily, from yesterday's lesson, we started seeing different families. So going from alkanes, which everything is single bonded, over to an alkene. We're only going to deal with molecules that only have one double bond. We saw how that double bond here introduces some unsaturation. We're not holding the maximum number anymore. And we saw every now and then you get that cis trans. Let's see how we do with these two examples here. All right, so let's try out a molecule. So sketch that for me there. I'm going to put a carbon group there and a bromine group over here. Okay. And let's do a ring compound just for practice. Let's throw a couple more carbons here. Let's do maybe an I group, maybe a C3H7 group there, and a F. Right. So again, I encourage you just to pause the video, try it out for yourself. All you're doing is you're trying to name the compound. Okay. After you've done that, you can just check your work with me here. Okay. So our naming always starts off with trying to find the longest carbon chain first. You can start from any side, go to any side. Again, the temptation is going to be, I notice that there's a double bond in these molecules here. I cannot start my carbon chain just because that's where the double bond is. I have to at least start from one of these sides here. Let's say I start from this side. I can go 1, 2, 3. No, that doesn't contain the double bond here. Let's actually count it around here. Should be able to count for me these 5 carbons. Okay. So we're definitely going to be a 5. Because the double bond takes priority, I'm going to count it left to right. And that way my double bond stretches between 2 and 3. If I counted the opposite way here, it would be between 3 and 4. It would be actually a 3-pentene, right? We're going to write this as the parent name first. So the very last word here, I'm a pent again. So 5 carbons long. Starting from position 2, that's where my double bond starts. So pent 2. ENE is now your ending. We're now going to be in the alkene family. And now aside from this sort of the parent that's circled here, we now need to name these 2 other groups here. Well, the BR, which is just the one atom here, this is going to be bromo, so B for bromo. This one here is a 1 carbon branch, that's going to be a methyl, and we already had numbered it, so just B for bromo comes first, so 3-bromo, 2-methyl, and then we have pent2ene there. All right? Now, because this one here is a double bond, we're just going to check one last thing here. Is it possible that this guy here has cis or trans? Again, to check cis or trans, I've already done most of the naming, okay? To check cis or trans, we're going to focus in on the 2 carbons where the double bond is, okay? I don't care everywhere else. Everywhere else is a single bond and they twist and they rotate, no problem, okay? In this case here, just the 2 carbons involved in the double bond, I want to see what these 2 carbons are holding on to. Now earlier we didn't call this one here a methyl group because that was actually part of the 5 carbon chain, but this carbon is kind of like holding a methyl that way, kind of holding a methyl that way. This carbon is kind of like holding a 2 carbon chain, so an ethyl this way and a bromine this way. What you're going to look for is for these 2 carbons involved in the double bond, are they both holding the same group? Earlier they were both holding, let's say, hydrogen or both holding fluorines or whatnot. In this case here, I wouldn't be able to tell the difference between this methyl going up or the methyl going downwards because, although I'm not physically breaking the double bond and trying to twist it, because I can't tell top from bottom, I can't distinguish whether it's going to be ethyl on top, bromine on bottom, or bromine on top, the ethyls on the bottom here. Let me just draw you that picture here. Let's say I had drawn what I may imagine. Okay, maybe this is the trans isomer here. When I look like this, okay, certainly if I actually interconvert, I would need to actually break that double bond. But because this methyl group here looks identical to this methyl group here, I don't know whether going from one molecule to the other, I had actually broken bonds to do the twisting or whatever, or I don't know if I simply just took this molecule here, looked at it from the opposite side. When I'm on the opposite side here, the bromine would then be on the top and the ethyl would be on the bottom. Because these are indistinguishable here, we're not going to need anything in front. We don't need any cis or trans there. So although we do want to check for the possibility of cis or trans, you're going to find examples of alkenes that sometimes they don't actually have cis or trans possible. Okay. Let's look at the second molecule here. Again, for simplicity, the ring is going to be our parent. We're only going to deal with one ring, only the double bond inside. So here we have 6-carbon chain. The double bond takes priority, so either I'm going to count it clockwise, 1, 2, 3, 4, 5, 6, going around this way. By stretching it around this way, I'm going to have the branches at 3, 4, and 6. If I try counting it the other way, again, the double bond has to stretch between 1 and 2, I would have a branch at 3, 5, and 6. Well, 3, 4, and 6 is a little bit tinier. So I'm going to prefer to count it, what I've colored in the black here. We do still need that word here, cyclo, to tell me we're a ring. Cyclo. Hex means we have 6 carbons in this linking here, 6 carbons in a row. We are in the alkene family. The alkene starts from 1, so cyclohexone. That covers everything in the ring here, everything in the black circle. And I still need to name the other branches here, the I branch, the F branch, this C3H7 branch here, and we just do that alphabetically here. So iodo, fluoro, propyl. So fluoro comes first. Using the black way of counting it here, we have 6. So 6 fluoro. We have a 3 iodo. And then we have a 4 propyl. All right. So that's pretty much how we name these structures here. Right. We've kept the numbers tiny. We made sure that the double bond takes priority. It takes the smallest number if possible. Right. Alkenes actually have a slightly different general formula. For an alkane, that's what we've been doing for the first part of the chapter here, we had CnH2n plus 2. Okay. For an alkene family, and we're going to even extend that in today's lesson here, as you go over to an alkene family, every time I start making double bonds, instead of everything being single bonded, remember I had to lose 2 arms, I lose 2 hydrogens. So because we're only going to assume things that have pretty much 1 double bond, again that double bond has to specifically between 2 carbons here, imagine losing these 2 on the end here. So the general formula for an alkene is going to be CnH2n. Technically, it's possible I can be a much larger structure here that actually has even more double bonds. Every time let's say I have 2 double bonds or 3 double bonds, I lose 2 hydrogens every time. We can track that loss of 2 H's every time I make that double bond there. By extension, in today's lesson here, we're going to visit the alkyne family. Fortunately, alkynes very similar to what we learned about alkenes. Alkynes are going to be a C triple bond carbon. And again, going from double bond to hydrogen, we need to lose yet another 2 hydrogens here, lose 2 other H's. If I only assume we have 1 triple in the entire molecule, this would then be CnH2n minus 2. So we're starting to see how the general formula might actually change. And again, we're just going to change the ending here. A and E for a single bonded family, E and E for double bond, and Y and E for triple bond. So just before we get to that here, let's just do one last double check here. We got most of the name here. We got the cyclo, we got the ring and all that. Again, only for a double bond, it's possible to have cis and trans geometric isomerism here. Let's zoom in and let's just look at the 2 carbons involved in that double bond there. Let's see what they're holding. Well, the carbon is holding that side of the ring, this carbon is holding this side of the ring. Those are very, very different. It's going to be really hard to compare there. In this case here, you'll notice though, this carbon is also holding an H, also holding an H. In this case here, the similar group that both carbons are holding are hydrogen. Because the hydrogens are implied to be sort of opposite each other here, pointing the same side to each other here, we're going to call this the cis isomer. So a fully correct name here will actually say cis, 6 fluoro, 3 iodo, 4 propyl. It is actually possible that not just all rings, all rings have to be cis, right? Well, it's possible, let's see if I can just do a quick sketch for you here. I could have this double bond here. I could have it almost be like a trans, where the hydrogens are across from each other, and yet this side here still ends up forming a ring. I have 4 other carbons, so maybe I go 1, 2, 3, 4. Okay. It is possible that something like that happens. Obviously, my bond angles are a little bit off, but it is possible. Just because I'm this ring here doesn't necessarily mean I have to be on the same side. Here we have an example of the trans form of the isomer. Exactly the same bonding, exactly the same elements attached in the same places, but this is actually the trans form of that molecule. Okay, so just look out for that. Only for alkenes, you might need to worry about sister trans. Okay. Continuing onwards now, today we're going to just finish off looking at these alkynes a little bit more. Again, I already just sort of alluded to that there. Alkynes, just the ending of the spelling here is going to be YNE. You will remember again, alkyne is going to be a triple bond. But specifically, where the triple bond has to occur is it has to be C triple bond to C. Because carbon has the equivalent of 4 unpaired electrons, I'm using all 3 of them to hold the neighboring carbon. That only leaves me 1 extra arm to hold something else, maybe hydrogen, maybe some substituent. The other one on the other side here also 3, and then I can hold only 1 more. This one here is going to be rigid, just like the double bond was rigid. So depending on which side, am I cis or trans or whatever, that could exist. But we're going to find that this is actually a little bit more simplistic. Unlike an alkene, which happens to have 2 attachments and I can compare, oh, are they the same side or the opposite side here, you find that alkynes only are glued to 1 extra thing. If you look at the geometry of this here, this is actually going to be just straight across. Whether I hold the hydrogen straight across here or maybe a fluorine straight across here, they're going to nonetheless be straight across anyways. So we're actually not going to get any cis or trans isomerism. So that's something a little bit simpler than even in the alkene family. Right. Let's see if we can practice a little bit of this naming here. We've actually done all the rules already, so we can just jump straight into it here. Let's go. So let's do 6 carbon chain. Let's sub on a bromo, maybe an iodo. Sure, let's just do that there. Exactly what we did with alkenes. Find the longest carbon chain, but it has to include the triple bond. This one here was fairly obvious. I just went straight across here. Okay, so that is a 6 carbon chain. We know our very last word in the name is going to be hex something. Okay, just like we do for our branches here, because our triple bond doesn't occur at position number 1, it's 1, 2, it's stretching between 2 and 3. We can actually go hex 2. But this time we're not in the alkene family, we're now triple bonded. This part here takes priority, this part here takes the lowest number. So it takes priority here, so we're actually going to be hex 2 YNE as ending. So that's actually going to be your parent. That covers everything that I've circled there. Everything else follows suit. We're going to keep the other numbers tiny here. So B for bromo comes before the iodo. Bromo is at 6, so 6 hyphen bromo. And then we're going to have 5 hyphen iodo. We just alphabetize the rest of the branches. If I have similar branches, we use di, tri, things like that. The numbers might be out of order in the word name. That's okay, right? But just for alphabetical sake, we do have the number, and we're now in the YNE, the alkyne family. Okay. So a couple of notes here. Parent must include the multiple bond. So it could be the triple bond, it could be the double bond. In the alkyne family, definitely could be triple bond. And we already said here the triple bond takes priority. So it may not necessarily be 1, but you do need to tell me where that triple bond here actually starts off. Okay. Let's try practicing going the opposite way here. Okay. So not too much variety I can add to this one. Let's see if you can draw for me the molecule here. Let's go 3 ethyl, 6 propyl, cyclo, let's do a hept, 1 ine. And yeah, sometimes you might see this one earlier. You might see it shown as cyclo 1 heptine, but definitely that one just tells you where the triple bond is starting. Okay. So see if you can give that molecule a quick drawing here. Okay. I know these names are starting to get really long really fast, but they actually contain a lot of information with how to draw this picture. Okay. So I always like starting off with the really end. The cyclo tells you have a ring. The ring is going to be your parent. Our ring has 7 carbons. We're in the YNE family, so I'm expecting C triple bond C. And the triple bond here stretches from 1 to 2. So we're just going to sketch 1 with the triple bond, that's carbon 2. 3, 4, 5, 6, 7. Okay. Doesn't have to be symmetrical or whatnot. Okay. Doesn't have to what looks like a sister trans, but again, we're not going to need to worry about that. Okay. So that covers the ring, it covers 7 carbons, it covers the fact that the triple bond here starts from position number 1. Because we're drawing it, it's totally up to us how we actually count it. So let's just count it down this way here. Again, the only thing you're not allowed to do, you can't go position number 1, notice other branches over here and go, oh, 1, 2, 3, still call this a 1-ine, because that ine here always has to stretch between 1 and 2. Okay. So we just erase that there. Okay. Again, for us, the ring by itself is going to be the parent. That's going to be the longest chain. The remainder of these here are holding hydrogen. So this carbon here has 2 H's. This carbon here has 2 H's and all that. Instead of having 2 H's like all the other molecules should have, this carbon here, position number 3, happens to have an ethyl group. And ethyl is a 2-carbon chain. I can either draw it with 2 carbons like that. The other one is holding a hydrogen there. Okay. And at position 6, we have a propyl group. Propyl meaning we have 3 carbons in a row, so 3 carbons just linked like that. Okay. So there we go. There's our molecule. Just for practice, I can show you this sort of skeletal structure here. We do have a triple bond. Whenever I have sort of the side of the molecule, that sort of implies that there's a carbon. As we look at the geometry in a later lesson here, we're going to actually see that triple bonds here only have 2 domains. They're actually linear. They're actually straight across. So we actually have the 2 other carbons. These 2 other carbons are actually directly across from it. And then we have holding 3 other carbons here. So we might go, let's say 1, 2, 3. Off position number 3 here. So 1, 2, 3. We have 2 carbons there. So I might kink 2 carbons off there. Off position number 6. So going around 1, 2, 3, 4, 5, 6. We're going to have 3 carbons in a row there. So this is actually the skeletal structure of the one that we just drew. That's all I would show. What's in the black here, how do you understand this here is every time there's a corner, there's a carbon. So the 2 carbons that are branched off like an ethyl, those are carbons there. It's understood everything else is saturated with hydrogens. Everything else is attached to H's. It's just probably this last little bit here. That's a kink here. Between the triple bond here, there actually are 2 carbons there. Yep, we still have 7 carbons in a ring, and we have that triple bond in between there. Okay. Let me make that note there. Although the triple bond here, although the triple bond is rigid, it doesn't allow for free rotation, it doesn't allow for twisting like a single bond does. Since both carbons only have 1 neighbor, they have 1 other attachment. So this carbon here is holding a carbon. This carbon here is holding a carbon. Okay? It doesn't have to be carbons, but they're only holding 1 neighbor. There's no sense of talking, let's say when we had an alkene, there's no sense of talking where, oh, are the hydrogens are they on the same side or are they on different sides? There's nothing to actually compare it against anymore. So because they only have that 1 neighbor, it is rigid just like a double bond is. That does affect its geometry and its reactivity and all that. Because of that, we don't need to worry about cis or trans. Okay, so there is no cis or trans. If you want the complicated definition later on, these are also called EZ isomers. Okay, there is no cis or trans isomerism. There is no same side or opposite side because they only have the 1 given neighbor there. Okay. So I'm just going to leave you with a couple molecules just for you to practice. I'm just going to sort of throw them all at you here. Okay. Let's draw. Okay. Let's draw it. Oops, it's appeared on me there. Okay. And then let's do a. These skeletal structures here always look very scary. Okay, if you need to, you can always add in all the carbons and whatnot. Okay, sub on a few different groups here just for practice. Okay, I've given you sort of 1 of each here. Okay, so if we have a molecule that everything is single bonded, that's going to be an alkane. Okay, If everything is double bonded, okay, or not everything, but if there is a double bond in the molecule, we're suddenly an alkene. We still have a lot of single bonded stuff around it. And if we have a triple bond here, we're actually going to be an alkyne. Okay. Keep the numbers tiny if you can. Keep these multiple bonds here in the parent if you can. Okay. If you need to, you can throw on all the carbons. So every time there's a kink, there's a carbon. Okay. If they don't specify what else is attached to it, like there's a kink here, there's a carbon, oh, then it goes to an arm here and it doesn't look like there's anything attached, that means there's a carbon there with its saturated 3 hydrogens on the side. In this case here, when I have that line there, it attaches to a bromine, so I know that is just to the Br. Bromine as a halogen group here, it doesn't have any extra arms, so it's just going to be just the one bromine there. Okay. So take a second, see if you can name through those. Just with more practice, you should be able to get more comfortable with these skeletal structures. For this top one here, because this one here is an alkene, you might need to check for cis or trans. Okay? And it is only the alkene that possibly has cis trans. The 2 carbons involved in the double bond, are they holding a similar group, both pointed the same way cis, or across from each other, are they trans? Okay? Thanks guys. If you have any questions, just let me know.